In this video we're going to find the value of this series. This is a famous series and we are going to transform this into a double integral that we will solve. This is equal to sum from 1 to infinity of integral x to the power n minus 1 from 0 to 1 dx, and then we also multiply this by another integral from 0 to 1 of y n minus 1 dy. Why am I doing this? Well, because if you integrate this function here, you will find 1 over n, and the same for this one. The integral is going to give you 1 over n. And when you multiply these two together, you will get 1 over n squared. And then you have to sum from 1 to infinity. Now, let's put these two integrals together. Sum from 1 to infinity of integral from 0 to 1, integral from 0 to 1, x times y to the n minus 1 dx dy. Now we are going to exchange the integral operator with the series operator. So we are going to put this summation here. We have integral from 0 to 1, integral from 0 to 1, and then here I have the series, and I can rewrite it with another index k. Instead of being from 1 to infinity, this is from 0 to infinity, and here I have x times y to the power k instead of n minus 1 dx dy. Now we have a geometric series. It's easy to find the value for a geometric series, so let me show you here. Instead of a series, I will consider a finite sum from 0 to n of some value z raised to the power k. This is just equal to 1 plus z squared plus dot 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 plus z to the n. And now there is a trick to find a formula for this sum, because I can multiply these terms by 1 minus z and divide by 1 minus z. In the numerator, when I multiply these terms by 1 and then I subtract these same terms multiplied by z, most of those terms will get cancelled, and the only two terms that remain are 1 multiplied by 1, if you take a look at it, and then you also have this 1 multiplied by z, whereas all the other terms will get cancelled. So I have 1 minus z to the n plus 1 divided by 1 minus z. And now if we let n go to infinity, and we assume that the absolute value of z is less than 1, we get that this is equal to 1 over 1 minus z. Now in this case, these two assumptions are almost satisfied. In particular, n goes to infinity because we have a series, not a finite sum. But this one is not really satisfied every time, because in our case z is x times y, so we have to assume that this mode is less than 1. If you take a look at it, x and y are between 0 and 1, right? So over this region in the xy plane, that's just a square whose sides are equal to 1, and almost at any point inside that region this inequality is satisfied, except when both x and y are equal to 1. So in this case, this less than sign is not satisfied completely, right? The series, when x and y are equal to 1, would diverge, but we might reason in the limit, where this one here is just a limit for x which tends to 1, so it would be something like 1 minus, and also this one, it would be 1 minus, not just 1. So you can consider it to be a limit, and therefore this inequality would be satisfied. But it doesn't really matter, okay? This is just something technical, not really important for the sake of the exercise here, for the sake of the problem, because we can solve that without being too careful about these limits of integration here. And also, it is just one point in a two-dimensional space, because the region of integration, as I said, is a square, something like this. This is x, this is y, and x goes from 0 to 1, and y goes from 0 to 1. So it's this region of integration, and the only point that we are going to discard is this point here, because it has coordinates 1 and 1, x equal to 1 and y equal to 1. But let's do more important stuff, right? We can calculate the series, and I can put the result here. So this is integral from 0 to 1, integral from 0 to 1 of 1 divided by 1 minus x times y dx dy. And now, in order to solve this double integral here, we will use a substitution. Remember that if we find the result here for this double integral, we will also find the result for the initial series over there, sum from 1 to infinity of 1 over n squared. We substitute x equal to u plus v and y equal to u minus v. Now we need to calculate the Jacobian of the transformation, so let's find the Jacobian matrix first. This matrix is given by the following components: dx over du, dx over dv, dy over du, dy over dv. And if you calculate those derivatives, they are quite easy to compute. We have 1, 1, 1, minus 1. And the determinant of this matrix, which I will indicate like this, is just minus 2. Now let's see how the region of integration transforms if we consider the UV plane. This is the XY plane, and as I said, we have this square. We have this side here, which is y equal to 0. Then we have this other side here, which is x equal to 1. And this other portion is y equal to 1. And this one here is just x equal to 0. This region becomes, in the UV plane. Now let's see. If x is equal to 0, this line here will transform. And you can find the transformation from here, because x is equal to u plus v. So if x is equal to 0, we have u equal to minus v. Then if x is equal to 1, this line here will transform. And from this equation, we find that u is equal to minus v plus 1. And also, let's consider y equal to 0. If y is equal to 0, from the second equation here we get that u is equal to v. And if y is equal to 1, we get u equal to v plus 1. Now we have to draw these four lines here on the UV plane. So let's draw first u equal to minus v. It is something like this. Now let's draw the line u equal to v. It is somewhere here. Let's also draw the line u equal to minus v plus 1, which is parallel to this one, and it is somewhere here. And then we have the line u equal to v plus 1, which is something like this. Now there are 4 points where these lines intersect, and the area enclosed by these lines is how the area enclosed by the square transforms on the UV plane. We can also find where these lines intersect each other. In particular, we are interested in these 2 points. This one, let me call it A, and this one, let me call it B. In order to find the coordinates of the point A, we need to intersect 2 lines, this one and this one. So those 2 lines are just u equal to v plus 1, and the other one is u equal to minus v. From this intersection we get that the u coordinate of the point A is equal to 1/2, whereas the v coordinate of the point A is equal to minus 1/2. And we also need to find the coordinates of the point B. Something similar can be done. We need to intersect the line u equal to minus v plus 1 and the line u equal to v. From this intersection, you get the point B, and the u coordinate of the point B is 1/2, whereas the v coordinate of the point B is 1/2. And now we are ready to rewrite the double integral that we have on the xy plane, integral from 0 to 1, integral from 0 to 1 of 1 over 1 minus xy dx dy. This will become like this. So first we will integrate over v, and then we will integrate over u. When we integrate over v, we need to go from this line to this line here until we reach the points A and B. The points A and B have the same coordinate u, so we have to split the integral into two parts, because when we reach these 2 points here, this first region will become different. It will become this one. So in this case, when we change the coordinate v, we will go from this point to this point, and the equations will change there. So we have these two regions. The integral, the double integral in the first region will become like this. We have to integrate over u from 0 to 1/2, because in this case, as I said, we are going from the coordinate u here at this point is 0, and then when we reach the value for a and b, it will be 1/2. And then we integrate from this line here, as I said, where we know that v is equal to minus u, so we have to integrate from minus u to this line here where v is equal to u, so we have to put u here. Then we have 1 over 1 minus xy will become 1 minus, so x times y, remember the definition for x and y here, so we have to multiply u plus v times u minus v, and here we will have minus u squared plus v squared. Then we multiply by the absolute value of the Jacobian, which is 2 dv du plus integral from 1/2 to 1. In this case, we have to move from 1/2 to 1 because we have to integrate over the other half of this area. Then we have to integrate from u minus 1, because we have to go from this line here where v is equal to u minus 1 there, and this one where v is equal to minus u plus 1. And then here we have 1 over 1 minus u squared plus v squared multiplied by 2 dv du. Now, in order to solve these integrals, let's first calculate the antiderivative of the inner integral, which is integral over dv divided by 1 minus u squared plus v squared. Now, if we make a substitution, we can define a new variable t where t is equal to v over square root of 1 minus u squared. If you make this substitution, you get square root of 1 minus u squared integral dt divided by 1 minus u squared 1 plus t squared, and this is equal to 1 over square root of 1 minus u squared integral dt over 1 plus t squared, which is equal to the arctangent of the variable t, and this is divided by square root of 1 minus u squared. And if you substitute back, you get arctangent of v over square root of 1 minus u squared, and then divided by square root of 1 minus u squared. Now, these double integrals here will become, so let me go here, we get 2 times the integral from 0 to 1/2 of, and here we have to evaluate this function between these two limits. So we have arctangent of u divided by the square root of 1 minus u squared minus arctangent of minus u divided by square root of 1 minus u squared, and then du divided by square root of 1 minus u squared, which comes from here. This is u, so please do not get confused with u and v, because sometimes my handwriting might not be too clear and you might mistake a v for u and vice versa. But I hope that when I read the formulas you understand if it is a v or if it is a u. And also we have to add another integral plus 2 integral from 1/2 to 1 of arctangent of minus u plus 1 divided by the square root of 1 minus u squared minus arctangent of u minus 1 divided by the square root of 1 minus u squared du divided by the square root of 1 minus u squared. Now we have 4 terms, but we can reduce these 4 terms to just 2 terms, because this term here minus arctangent of minus u over square root of 1 minus u squared is just equal to the arctangent of u divided by the square root of 1 minus u squared, since the arctangent is an odd function. And similarly for this one, because this term here will just be exactly equal to this one. So this is arctangent of minus u plus 1 divided by the square root of 1 minus u squared. And therefore we have to calculate 2 integrals. One integral is the integral of that function. So we have to calculate integral of arctangent of u divided by the square root of 1 minus u squared. And then we also have du divided by square root of 1 minus u squared. And we can calculate this integral by using a substitution. In particular, we are going to substitute for this function the variable s, which means that we have tangent of s equal to u divided by the square root of 1 minus u squared, and from here we can rewrite 1 minus u squared, which multiplies tangent squared of s equal to u squared. From here you can solve for u, you get u squared equal to tangent squared of s divided by 1 plus tangent squared of s. But 1 over 1 plus tangent square of s, you can easily calculate it. You can see that this is equal to the cosine squared of s, and therefore we still have to multiply by tangent squared of s. But this is equal to the sine squared of s. And from here, we can choose for the variable u this solution, u equal to sine of s. So you have to be careful here, because when you take the square root, you have either a plus or a minus sign. And I will skip some details here. If you want, you can do your own exercise and try to understand more in depth this step. But anyway, if you go on, the differential of u is equal to the cosine of s times ds. And therefore, this integral here will become, let me do it here, this is just equal to integral of s times cosine of s ds. And then we divide by this square root here. We have the square root of 1 minus u squared, but u is sine s, so we have sine squared s. But square root of 1 minus sine squared s is just a cosine, so we can cancel this one with this one, and therefore we have the integral of s ds. But that's just s squared over 2. And s, if we substitute back, we get 1 over 2 arc tangent squared of u over square root of 1 minus u squared. And this is one integral, but we also have to calculate this one. So we have integral of arc tangent minus u plus 1 divided by square root of 1 minus u squared du over square root of 1 minus u squared. We are doing exactly the same, so we are going to call this function s. This is the substitution that we are going to make. So the tangent of s will be equal to minus u plus 1 divided by the square root of 1 minus u squared. And from here, if you take the square of this, you get 1 minus u squared. Tangent squared s equal to 1 minus u squared. From here, if you simplify a little bit, you get 1 plus u times tangent squared of s equal to 1 minus u. And from here, you get, if you solve for u, tangent squared s minus 1 equal to u times minus tangent squared s minus 1. Now we divide both sides by this term, so we will find the solution for u. U equal to minus tangent squared s plus 1 divided by 1 plus tangent squared s, and we know that 1 plus tangent squared s is 1 over cosine squared of s, so we get cosine squared of s times 1 minus tangent squared s, and from here we get cosine squared s minus sine squared s, but this difference is just the cosine of 2s, if you remember your trigonometry, and therefore du will be equal to minus 2 sine of 2s ds, and the integral above is equal to integral of s times minus 2 sine of 2s, and then we divide by the square root of 1 minus u squared, which is 1 minus cosine squared of 2s ds, but sine of 2s will cancel this term because the square root of 1 minus cosine squared of 2s will be sine of 2s, and therefore here we have to integrate minus 2s, which is minus s squared. But if you remember the definition for s, we have minus arc tangent squared of minus u plus 1 divided by the square root of 1 minus u squared. And finally, now we can write down the result, because this term here will become, so let me do it here beside, we have 2 times the integral from 0 to 1/2 of 2 times the arc tangent of u over square root of 1 minus u squared, u over square root of 1 minus u squared, and then we have plus 2 times integral from 1/2 to 1 of 2 times the arctangent of minus u plus 1 over square root of 1 minus u squared du over square root of 1 minus u squared. We have already calculated these integrals here, so from here we get 4 times the result of the first integral here, which is 1/2 arctangent squared of u divided by the square root of 1 minus u squared, evaluated between 0 and 1 over 2, plus 4 times minus arctangent squared of minus u plus 1 divided by square root of 1 minus u squared evaluated from 1/2 to 1, and this is just equal to 4 times 1/2 arctangent squared of 1 over square root of 3 plus arctangent squared of 1 over square root of 3. If you evaluate these terms, you get 6 times pi over 6 squared, which gives you pi squared over 6. And this is the result of the famous series that we had in the very beginning. This series here, and therefore this is also the result for this integral here.